This is the second video about slope fields, which, as I said in the first video, gives you a graphical way of seeing what solutions to equations like this are going to look like. And the idea, again, was that you've got a plane. I can draw it. And for any point t comma y or x comma y in the plane, no matter where you pick it, you can plug that point into the right-hand side. Whatever number you get out, let's pretend it's -1, you make a little mark in the plane whose slope is equal to that value, in this case -1. And the differential equation says that solutions have to follow the slope field in such a way that the slope of a solution curve is always equal to the value of the right-hand side anytime you pass through the middle of one of these line segments. In this video, I want to illustrate how to use Mathematica to make slope fields. And I will also illustrate what you can do with the CD-ROM. But mostly I'm going to focus on Mathematica. I think that will be a little easier for you to see here. We can get zoomed in. There's a very important thing that you realize that needs to be done before you can use Mathematica 6 to make slope fields. With Mathematica, if you've got version 5, it's a little bit different. With version 6, you need to make sure you type in and enter the following line. You make two less than signs, and then you type VectorFieldPlots with a capital V, capital F, capital P, and then you put a little backwards slash there. What this is doing is it's going to load a package that will allow you to make vector fields. It's done so that you can sort of save space. Mathematica has sort of some commands hidden behind the scenes that need to be loaded before you can use them. And VectorFieldPlot is an example of such a package that needs to be loaded before it can be used. Now I'm going to use a command, VectorFieldPlot, to make slope fields, and in the future we'll use it to make vector fields. Again, Mathematica is very case sensitive. You've got to use a capital V, a capital F, and a capital P and put all those words together like you see there. Let's take the first example that we considered from the previous video. That was dy dx equals x. Or let me go back and I'll use t's when I do it on Mathematica. dy dt equals t. What we need to do to make the vector field that we saw in the last video for that particular differential equation is, in a sense, enter the vector field inside curly braces with a comma in the middle. The first entry in this list before the comma for slope fields will always be a 1. When we get to chapter 2 and beyond, and we create true vector fields, that won't always be a 1. What comes in the second part of this list, the second element of the list, is the right-hand side of the differential equation. And if my differential equation is dy dt, that means I want to put a t after the comma, because that's my right-hand side. I need to specify what kind of interval I'm going to plot this over, and I guess like the overhead projector, I think I went from -4 to 4. On that, I'll do the same thing here. If you try entering this command without entering the first command, loading the VectorFieldPlots package, you won't get any output from it. But once you've loaded that VectorFieldPlots package, now we should get some output. And here it is. There's my output. It's a graph. And notice it does kind of look like the slope field that I showed you on the transparency from the first video about slope fields. It does look similar. It's not exactly the same. For one thing, they're arrows instead of line segments. Well, there's nothing we can really do about that. Mathematica just makes arrows, and we have to get used to that. It's because Mathematica thinks it's drawing vectors instead of little line segments. Another thing that we notice is that they all have different lengths. I can scale all these to be the same length with a special command. Put a comma after the ranges for t and y, and type the word, the command scale function, capital S, capital F, and then put a minus sign and a greater than to make an arrow. And this is kind of funny, but I don't quite understand what it does, but we'll just do it anyway. Inside parentheses, you put a 1 and, like that, with the symbol for and. This should make all these line segments have the same length. And there we go, it does. What else is different? Well, we don't have any axes in here. And there used to be a command with previous versions of Mathematica that worked inside the command for vector fields to put axes in here. But I tried it recently, and it doesn't seem to work here. It's axes, arrow, true. It didn't put any axes in there. Well, I found a way to get around the fact that it doesn't seem to work here. If we use the command show out in front of this plot, and put the axes true not inside these square brackets for the VectorFieldPlot command, but instead really inside ultimately the square brackets for the show command. If you're confused about what that means, you should take a look at this command carefully. I've got two commands that are nested. I've got VectorFieldPlot sort of from the start of the word vector field to the first end square bracket, and then I've got sort of the show outside of that. The VectorFieldPlot command gets done first, and then the show command second. You work from inside out. That's sort of a little trick that will get the axes in there for you. There we go. So there we see the axes. We can also label the axes. And these are all things that would be, generally speaking, good for you to do when you're making graphs. If I want to label the horizontal axis with a T and the vertical axis with a Y, I have to type that. Axes label, capital A, capital L. Put T and Y inside quotes, inside a list, separated by commas. And now the axes are labeled. See a T there over on the right and a Y up on top. If you don't like how big Mathematica made it, you can actually change the size, the font size of those, by just highlighting those things, going up to Format, and text size. It's 12 point by default. We can go up to, say, 16 point. It makes it bigger there. And it's also going to make it bigger in the plot. So there you see the T and Y are now bigger. So you can do lots of things to make your graphs look prettier. One other difference we note here is that Mathematica makes these line segments have the correct slope at the base of the arrows, not the middle of the line segments. For example, when t is 0, along the y-axis here, I'm not making little line segments centered at t equals 0. Rather, Mathematica is making little arrows base at t equals 0 with the correct slope. So that's just something to realize. The solution curves, therefore, technically don't pass through these arrows in the middle with the correct slope. They pass through the base, the start of the arrow, with the correct slope. Could I verify that a function is going to pass through this with the correct slope? Yeah, for example, I already said that in the previous video that the general solution to this differential equation is, well, with t as the independent variable, it would be 1/2 t squared plus c. let me just go ahead and plot a couple of those functions. For example, I'll plot 1/2 t squared itself and maybe 1/2 t squared plus 1 in a plot that I'm going to call plot 1. There we go. And now I can use show to put that plot on top of the vector field. I'll put it after this n bracket of the vector field plot. I'll put it in here. There are probably different places that I could put it. I'll put the name of that plot back up here at the top. I gave that plot a name. I called it plot 1. That graphic object has name plot 1 that I can refer to now. Just like variables can represent numbers in Mathematica, variables can represent graphic objects. And I think this should work. Let's try it. Nope, didn't like it. Let's see. I'm glad this happened. You will have plenty of frustration with Mathematica too. And sometimes you just need to keep experimenting to see if you can come upon something that works. Maybe it doesn't like the fact that I'm mixing my plot names with those different commands. I'm going to try putting plot 1 before the vector field plot command. And I also need a comma back here. Let's see if this works. I'm not sure. Well, it kind of worked. Though, notice it changed the range of the plot for the y-axis. I can force it back into that same picture that I had before by doing this. I can go and type in plot range. Some of this ends up being kind of redundant, but to make it work, you kind of have to do anything you can to make it work sometimes. Plot range, capital P, capital R, arrow, and then inside I've got a list of lists here. The elements of this list are themselves lists. This -4 to 4 is the t range. This -4 to 4 represents the y range. Now it should force everything into that window, and it does. Though something else changed. We're getting a great tour de force here. Now it's sort of scaled differently. It's kind of squished a little bit. It's no longer kind of shaped in a square box there. If I add another command, aspect ratio arrow 1. I didn't spell that correctly. Aspect. That should force it into a square box. And there we go. Seems like a lot of work. And it is a lot of work. It's a lot of frustration that people encounter with this kind of thing. But it's important. And those curves are kind of dim. I don't know if you zoom in, if we can see those better. Those are solution curves, and it should seem reasonable that they are passing through the base of those arrows with the correct slope. For example, if we look at this one, it's pretty close. This one looks like it actually might be off a tiny bit, but I guess that's pretty good. It's hard to say for sure, but it's certainly reasonable, okay, that this matches up. So this illustrates some of the frustration that you have already encountered or will encounter with Mathematica. And it illustrates also that you should watch these videos to get some insight. And I also have these Mathematica files section by section and from the text that you should make sure you read carefully. And you should use the help browser to help you with things. And you should come and ask me questions in my office hours. Those are all different things that you can do to try to learn how to use this program. Let me show you something else that you can do that's kind of nice. Once you've got it working, you can make changes very easily. One thing you could do if you want to keep this plot in your file is you can just copy and paste the whole command. I'm highlighting the entire cell over here on the right. The graphic disappeared. There it is. I have to double-click even further to the right to get that to come back. If I highlight the blue cell over on the right, Or if I just highlight the entire command, I can copy and paste that command further down if I want to keep the graph there. And I can re-enter it if I like and get the same picture. Or I can change the picture because I can change the differential equation, for example. Let's go to the second example that we considered from the previous video. dy dt equals y. Solutions of that are going to be constant multiples of e to the t. Change the t to a y. Now we should get arrows whose slopes are constant along horizontal lines. I just changed that t to a y. That's all I did. I probably should get rid of the plot 1, though, or change that, because those are no longer going to be solutions. Maybe I'll go up here and I'll copy and paste this plot 1 command down here. You've got freedom to put these things in different spots. Copy and paste it there, and I'll change the functions inside here. I'll change them to being multiples of e to the t. Let's try e to the t itself and say 2 times e to the t. I'm using a capital E as my number e. I also could use the palette, the basic math input palette, over here. That's what I typically do, actually. Even though typing a capital E is faster, there's a number E, a special fancy number E that could be used also. What you do not want to do is just use a little e by itself, a regular little e. So there's the new plot 1 with e to the t and 2 times e to the t on it. And now if I go back, Mathematica will remember that that's the new plot 1, and it will plot those new functions in the slope field here. And you can see they are following the slope field pretty well. What other examples have we done from the previous video? We did dy dt equals, I think it was 2y minus y squared. Had equilibrium solutions at y equals 0 and y equals 2. I think I'll get rid of the plot 1. I don't want to bother finding the solution of that equation. We'll just look at the slope field itself. There it is. Notice slope marks are horizontal along y equals 0. And you don't see at y equals 2 that they're horizontal because it didn't plot the ones at y equals 2, though you can see above it the ones they're going down, negative slope, and below it they're going up, positive slope. We could probably force more arrows into this picture, more slope marks, by adding another command in here. Plotting more points in the diagram. I think the default is to plot sort of on a 15 by 15 grid. So if I increase this to say 30 or 20 even, it should plot more line segments, though it does take a little longer. You've got to be patient. There we go. And here we see that we are pretty close to plotting some line segments along the line y equals 2. Not exactly, but pretty close. There's the slope field. You can really see the pattern pretty well. That's the nice thing. 2 more quick examples from before. dy dt equals x minus y, or in this case t minus y. There, that's non-autonomous. The equation was. And the slope field is not constant along vertical or horizontal lines. And you might remember this if you saw that video, this picture before. And finally, there was the dy dt equals t squared minus y squared. You can see that one too. There we go. Very nice picture. A couple other things I just want to mention before I end this. The idea of a slope field, like I said, is very important for helping us understand vector fields when we get to chapter 2 and beyond. It's also important for helping you really understand what Eulers Method is all about from section 1.4. Eulers Method is what's called a numerical method for solving differential equations. And the basic idea is related to the idea of a slope field. So make sure you really think about how slope fields and Eulers method are related when you do use Eulers method. Finally, this is, I know, harder for you to see, and we might have to zoom in closer. It's even a little bit blurry for me on the screen. But I just want to illustrate that you can make slope fields for first order differential equations on here. Let's see, it's HPG solver is one common thing that you will use. And I know that you probably can't see this, but what's right here is the differential equation. This says dy dt right here, and what's typed right here is actually a y minus t. I'm going to change it to a t minus y, so it's the same as the one we already looked at. And so that's entered now, and we can show the slope field by clicking Show Field. There it is. It's kind of dim, but perhaps you can see that it really is the same as the slope field from before. And I can click on this to draw in some solution curves. And there we see the solution curves from that equation, dy dt equals t minus y, that we've already illustrated before. So you'll want to experiment with that a little bit. That's a nice quick way. It's quicker than Mathematica to get an idea of what slope fields look like. And you can also have some fun with it. There's something called target practice that I enjoy. The equations are kind of pre-specified. Your choices are over here. The particular equation we're looking at now is dy dt equals y squared minus t. And the thing that's kind of fun with this is you set a target, maybe right there, and then you try to hit the target. So it's like target practice is what it's called. You want to pick an initial condition over here that you think, where you think the solution curve through that point is going to get close to your target. And it's kind of hard to get very good at this, but I'll try. Oh, way off there. Well, too low there, so now I've narrowed it down. It's got to be somewhere in here. Getting closer, but you know, these initial conditions are notoriously sensitive. These two left-hand ones are very close together yet at the start, but at the end they're very far apart. So it's real hard to pick one in here. Let me just try one more there. Got pretty close that time, but to get closer I'm probably going to have to try an initial condition up here. Or go closer. There I'm close enough that the computer thinks that I've basically finally hit the target. Close enough within experimental error to get that target. So this is something to make sure you do and experiment with and even enjoy. This is kind of fun to get the computer to draw these slope fields and to draw in solution curves, and I hope you take the time to do that.